We have seen one use of locality-sensitive hashing where the underlying data is a collection of sets, and similarity means Jacquard similarity. But there are other approaches that share the same goal of focusing our search on the pairs that are likely to be similar. We're now going to see some of these variations. Later we'll examine general techniques and definitions of similarity other than Jacquard similarity, and we'll see that LSH is really an approach to problems rather than a particular algorithm. Our first example of using LSH concerns a problem called entity resolution. In this kind of problem, we're given a collection of records. Each record provides some information about an entity. Typically, entities are people, but they could be companies, physical locations, events, or any number of things. The entity resolution problem is to determine which sets of records refer to the same person and to merge these records into one record that tells everything about that entity. The problem is way more complicated than it looks. For example, it is typical that records about people include the name of the person, so it looks like it should be no problem at all to group them into sets that represent the same individual. But in a large collection of records, there will be people with the same name, so grouping by name will merge records for different people. And worse, the same person may have the name written in different ways in different records. Some records will have their middle initials and others not. A person's nickname may appear in one place and their formal name in another, like Sue and Susan. And of course, misspellings occur, which makes names look different even if they are intended to be identical. And we often can compensate for these discrepancies by using other information in the records. For example, two records may have similar names but identical phone numbers or identical addresses. That's when the problem becomes really interesting. I'm going to tell you a real story of how I used LSH to get a big consulting fee. After I retired from Stanford, I took a job consulting for some lawyers. They were dealing with a lawsuit involving two companies that I'll call A and B. Company B had a service, and Company A agreed to use its customer base to find customers for Company B. But the companies took to squabbling, and the deal was eventually canceled. Since B was serving many of the customers that A had sent them, A was owed fees for these customers and sued to get those fees. Unfortunately, neither company had bothered to modify their records to indicate whether a customer had been part of this deal. A could have created a record, "We sent this guy to B," and B could have added a bit to their record saying, "This guy came from A." But neither did. So they had to pay me to figure out how many customers appeared in the databases of both companies. To set the scale of the problem, each company had about 1 million records that might represent a customer that A had provided to B. That's a tiny database by today's standards, but notice that there are 1 trillion pairs of records, one from A and one from B, that might be the same person. It is way too expensive to examine and evaluate 1 trillion pairs of records. Each record from either company had a name, address, and phone number, but often these were different even for the same person. In addition to typos and the sorts of variations in name we discussed earlier, there were many other sources of difference. People would move and tell one company their new address, but not the other. Area codes would change even though the rest of your phone number remained the same. People would get married and change their name. In all these cases, one company might track the change and the other not. So our first step was to devise a measure of how similar records were. We gave 100 points each for identical names, addresses, and phone numbers, so 300 was the top score. Interestingly, only 7,000 pairs of records received this top score, although we identified over 180,000 pairs that were very likely the same person. Then we penalized differences in these three fields. Completely different names, addresses, or phones got 0 score, but small changes gave scores close to 100. For example, if the last names were the same, but there was a small spelling difference in the first names, like this, then the score for the name would be 90. If the last names were the same, but the first names completely different, the score for the names would be 50. We scored all candidate pairs of records and reported those pairs that were above a certain threshold as matches. One of the subtle points is how we set the threshold without knowing ground truth, that is, which pairs of records really were created for the same individuals. Notice that this is not a job you can do with machine learning because there's no training set available, and we'll talk about how we did this soon. Okay, so as I mentioned, we can't afford to score all trillion pairs of records. Okay, so I devised a really simple form of locality-sensitive hashing to focus on the likely matches. Here we used exactly 3 hash functions. One had a bucket for each possible name, the second had a bucket for each possible address, and the third had a bucket for each possible phone number. Now the candidate pairs were those placed in the same bucket by at least one of these hash functions. That is, a pair of records was a candidate pair if and only if they agreed exactly in at least one of the 3 fields. Did we lose some pairs? Surely we did, because there would be some pairs of records that had small differences in each of the 3 fields, and these would never become candidates for scoring. We actually did a hand sampling of records and estimate that there were about 2,500 pairs of records that we missed, but that's not bad compared with the 180,000 that we found. And finding those extra 2,500 would probably have cost more than they were worth to either company. You may have been puzzled by my remark that we hashed to one bucket for each possible name, since there are, in principle, an infinite number of possible names. But we didn't really hash to buckets. Rather, we sorted the records by name. And then the records with identical names appear consecutively in the list, and we can score each pair with identical names. After that, we resorted by address and did the same thing with records that had identical addresses. And then finally, we repeated the process by sorting by phone number. We should observe that another approach was to follow the strategy we used when we did LSH for signatures. We could hash to, say, several million buckets and compare all pairs of records within one bucket. That would sometimes cause us to look at pairs of records with different names that happen to hash to the same bucket, but if the number of buckets is much larger than the number of different names that actually appeared in the data, then the probability of collisions like this is very low. Now remember that we scored each candidate pair of records, but suppose a pair gets a score like 200 out of 300, indicating a good deal of similarity, but not perfect similarity. Do these records represent the same person? Well, turns out a score of 200 made it very likely that the records represented the same person, but how could we tell for sure? We devised a way to calculate the probability that records with a score X represented the same person, and it's worth telling about because it can be used in other circumstances as well, even though the data we used was very specific to the problem at hand. First, remember that there's a gold standard. 7,000 pairs of identical records that we could assume represented the same person. For these pairs, we looked at the creation dates at companies A and B. It turns out that there was a 10-day lag on average between the time the record was created by company A and the time that the same person went to company B to begin their service. On the other hand, in order to reduce further the pairs of records we needed to score, we only looked at pairs of records where the A record was created between 0 and 90 days before the B record. Now, if you take a random A record and a random B record, where the A record happens to have been created between 0 and 90 days before the B record, you'll get an average delay of 45 days. These records are almost certain to represent different people because they were chosen at random. So let's look at a pool of matches, say those with score 200. Some will be valid matches, and their average difference in creation dates will be 10. Others will be false matches, and they will have an average difference in creation dates of 45. Suppose that within this pool, the average difference is X. A little math tells you that the fraction of matches that are valid is 45 minus X, all divided by 35. So for example, if X equals 10, then this fraction is 1, which makes sense, since 10 is the difference that the gold standard provides. If X equals 20, then we would expect that 5/7 of the matches are valid. That makes sense. 5/7 of the matches will have an average difference of 10, and 2/7 of them will have an average difference of 45, so the weighted average of the averages is 20. So we tried to convince the lawyers that they should go into court with a claim of a fraction of each of the pools that had average delays less than 45, even though we couldn't tell which pairs in each pool were valid and which were not. But the lawyers told us not to even try because no judge or jury would understand the argument. But you understand it, don't you? Well, while we use the creation date field in records, the idea generalizes to use any field that was not involved in the locality-sensitive hashing. All we need to know is that the value in this field will be closer when the records represent the same entity than when they represent different entities. That should be the case almost always. Okay. For a concrete example, suppose records represent individuals and they have a height field. We can assume that if the records represent the same person, the average difference in heights will be 0, or perhaps more precisely, the difference will be the average measurement error, which we can determine if we have some gold standard of records that we know represent the same person. This difference substitutes for the difference 10 days in our example. But if two records represent different people, then the average height difference will be the average difference for random people. We can determine this difference by picking a relatively small number of pairs of records at random and determining the difference in heights in those two records. This difference plays the role of 45 in our example.